So a very excellent question concerning this concept of a derivative of a vector valued function is, when you take the derivative of a vector valued function, what do you get? Well, the result, r prime of t, is a vector tangent to the curve, of course at point t, and pointing in the direction of increasing parameter. In other words, pointing the way that the curve that's being drawn is increasing. This picture here shows the vector r of t is this purple vector. The blue is representing the vector valued function, the graph being drawn by the vector valued function, and at this particular value of t, we've got the derivative vector pointing out in this direction. And of course, since it's a vector valued function, this vector could be the same, could be anywhere. Any parallel vector to that is the same as that. But you could think of it as, what would be happening with the vector at this point? How is it increasing? What direction is it pointing in or moving in at that particular time? So that's the geometric interpretation of r prime of t. And here's an easy example. Find the derivative of each vector valued function. R of t is 2t minus 5 plus 3t squared I plus 3t squared plus tj. So r prime of t, 2i plus 6t plus 1j. This one, it's going to need the product rule, right? So I guess first d second e to the t times cosine t plus e to the t times sine t, all that times I. And then this one is going to be negative e to the t times sine t plus e to the t times cosine t times j. And then the last part here for the k, we're going to need 1 over t times k, and of course we have to have the restriction that t is a positive number, because ln of t wouldn't be defined for negative, and of course 1 over t is not defined for 0 either, for that matter. But these guys, they were okay for any values, but this one is restricted. So there's our answer, and there's our restriction.